Okay, this is a continuation of our problem, and we want to now graph f and f inverse of x. So this is my f of x, if you remember from our original problem over here. This was what it was. If f of x equals 2x minus 4, find f inverse of x, verify, and graph both functions. Okay. And I try to write this in blue and this in green so we can see what they look like. So f of x is pretty easy. If we put this in slope-intercept form, we know that the slope, m, equals 2, and the intercept is negative 4. So we'd say b equals negative 4, or it goes through the point 0, negative 4. So it's pretty easy to graph if we got graph paper. Now this one, f inverse of x, was written like this, and it may not be too obvious how to graph it. So what I did was I broke it up. I wrote x over 2 plus 4 over 2. We can do that. This is a common denominator, so we're kind of going backwards. And then x over 2 is the same thing as 1/2 times x. And then 4 over 2 is 2. So now I have this in slope-intercept form. And I can tell that the slope is equal to 1/2. And b, in this case, would be equal to 2. That means it goes through the point 0, 2. So let's graph both these and see what they look like. And I've got some graph paper here. I'll graph, first of all, f of x, and I'll label it. So the intercept is negative 4 and the slope is 2. So there's my intercept, negative 4. And my slope is 2. So I go up 2 over 1. Up 2 over 1. Up 2 over 1. Oops, that was 3. I missed that there. Sorry about that. I think I got my white out here. Excuse me. You probably shouldn't use ink, but I doing these in color so you can see. So up 2 over 1, up 2 over 1. So I got 3 points, so that should be enough. So now I'll use my ruler and all right, and this is the 2x minus 4. So this is f of x. Now let's do the inverse. And this is going to be 1/2 x plus 2, so my intercept is positive 2. And my slope is 1/2, so I go up 1 over 2. Up 1 over 2. Up 1 over 2 like that. And I'll connect these. And this is my f inverse of x. F inverse of x. All right? So now we graph both those functions. Now this is the interesting thing about these things. If we have two functions that are inverses, all right? I guess I should have labeled this over here. F of x, excuse me. So this is f of x and this is f inverse of x. And if we look at the line y equals x, which is actually the identity function, y equals x, in other words, the x and the y are the same, and we plot this, if we plot this line y equals x, so we know that 1, 1, 2, 2, 3, 3, 4, 4, we draw that line, that nice diagonal line that goes right through the origin. And this is the line y equals x, our identity line again. Then we can see that these are symmetrical. In other words, if I've got this point over here, which is the point 0, 2, I have the point 2, 0. And we know that that's the way the inverse functions work. If 2, 0 is on f of x, then 0, 2, just reverse those, is on f inverse of x. So they're symmetrical to this line. That's always going to work out. So they're always symmetrical. What's this point? This point is the point, just to give you an example, this point here is the point -4, 0. And this point over here is the point 0, -4, you see. If 0, -4 is on the function, -4, 0 is on the inverse. And they're on the opposite sides of this line. And you could kind of look at it like this. If we just drew a line connecting those 2 points. Oh, we were careful with this. Or a segment, a line segment connecting those 2 points. You can see that this distance from this point to our y equals x is the same as the distance from y equals x to this point. So they're symmetrical, and that would work for any 2 corresponding points. There's a couple there. They're all over the place. All right, so that's a interesting characteristic of inverse functions. And they don't have to be lines, they can be curves, and we'll do some more sophisticated problems later and see those. Okay, I hope that helps.